Okay, so today we will be doing the power method for finding the largest eigenvalue. We will be developing actually the C program code for it. And this is the theory which we have already discussed. Ki what we have to start with, a matrix will be given. Okay, we have to guess the eigenvector initially. Okay, so suppose I say ki xk is the eigenvector guess, then you multiply a with xk, that is axk, it becomes yk plus 1. Then you just find out the largest, numerically largest, that means magnitude, considering the magnitude is the largest component of yk plus 1. Whatever you get, you divide the yk plus 1 vector, eigenvector, by that one. That means actually you are normalizing the vector. Then that becomes your next guess, xk plus 1. So what you will do, once you get xk plus 1, again you perform this one. Key, you multiply or you perform the multiplication a of xk plus 1. That again becomes your yk plus 1. Then again you find out the largest in sense of magnitude component of yk plus 1. Then again you normalize it, and then again it becomes the next iteration level eigenvector. And this continues until and unless the accuracy level is reached. So we have to start with a guess, initial vector guess. Okay, acha, this is the what we have done for the, or just consider the power method. But one thing more we have to consider here, ki the failure of the power method. For the failure of the power method, what it is saying, ki suppose the initial column vector, that means the initial eigenvector which you are starting with, is just the eigenvector of the given matrix. Suppose the initial guess you are making exactly the eigen, you are guessing exactly the eigenvector, one of the eigenvector of the matrix itself. Okay, then what will happen? So suppose I am just guessing it, then what will happen? Ki this power method will fail in that case. Why do I say will fail in that case? For example, let me just consider ki this is my matrix. Okay, I will also show it once I run it in the program. You can check it on your own, or you can check by hand also. Suppose we have just calculated it manually ki these are the eigenvalues. Okay, and suppose I consider the eigenvalue 1 corresponding to this, the eigenvector is 1 0 0 0. Okay, but as you can see, 2 is the largest eigenvalue. So suppose if I give my initial guess as 1 0 0 0, that means if I guess, if put as an initial guess the eigenvector corresponding to this eigenvalue, what will happen? It will give you the output eigenvalue 1 and the eigenvector 1 0 0 0. That means it will converge in one iteration. Okay, actually it will not at all compute. So this is a failure, a big failure of the power method. Okay, so while we just run or design the program, what we will do, we cannot tackle it because it is the fallacy is in the program a method itself. What I will do, I will just introduce a check step in the programming. What will that check step do? It will just check, or it will just check key whether you are getting, or your method is converging in single iteration. If it is converging in single iteration, then there is a possibility key your method is not at all giving you the largest eigenvalue and corresponding eigenvector. For suppose why I am saying it may not give, because there is a chance it in some cases it will give. For example, if I put the eigenvector, initial eigenvector guess as 1 0 1 0 0 0, this if I put the initial guess, then it again converges in one iteration, and you get the eigenvalue 2, and 2 is indeed the largest one. So okay, for that initial guess it is working. So it may work, and as I gave the previous example, if I start with initial guess 1 0 0 0, which is the eigenvector corresponding to 1, this one you may check, then what will happen? It will again converge in one iteration only, and the eigenvalue, largest eigenvalue as given by the power method, will be 1. But that is not true, it is true actually here. So that if the power method is giving you the output in only a single iteration, after running a single iteration, then that is an indication that the power method is not at all running according to what, according to the normal condition. Okay, so that means what, it is not giving you, or it may not be giving you the correct input, because how do you know whether the initial vector which you are entering is the eigenvector corresponding to the largest eigenvalue? You never know. Okay, so that may give you a wrong result. So as soon as your program converges in a single iteration step, the code will give you the output key, the program may not be running properly. Program means the power method itself is may not be running properly, so you just rerun the program using a different initial guess of the eigenvector. So that check step will be there in the program itself. Okay, So that is the thing. So let us now go to the programming part and see how we are developing the program. So the basic thing is to keep this formula or give this strategy in our hand, this one. You start with the initial guess, you find out a of xk, a of x0 if you are starting with the guess x0. Then the next vector what you are getting, you find out the largest magnitude largest of the component, okay, and then you divide it and then becomes your next guess, and this continues until and unless what, the accuracy is reached. Now the accuracy is twofold: one accuracy for the eigenvalue accuracy, another one for the eigenvector accuracy. So we have to take care of both of them simultaneously. Acha. Now let us go to the programming part. So this is a standard starting one, okay. Acha. Before we enter into the main program, what we are doing here, we are just developing a auxiliary program here, or auxiliary function rather. Auxiliary function is doing what? See, as I said, you have to find out the largest component, okay, largest in sense of magnitude component of the eigenvector in each step. So finding out the largest component, suppose it is a column vector of 4 component column vector, so you have to find out the largest of this. So this finding out the largest is to be done in each and every iteration step. As you can see here, every time you are constructing this xk plus 1, multiplying it with a, developing this yk plus 1, then you have to check for the largest component. So that part will be handled by this auxiliary function, find max function. So what this find max function is doing, it is taking any array, okay. So suppose I have given 10 here, okay, just that actually how many numbers you need here, you need corresponding to the dimension of the matrix. If it is a 5 cross 5 matrix, then the eigenvector will be a 5 cross 1 column vector. Okay. If it is 6 dimensional, then 6 cross 1, that means 6 dimensional column vector, and likewise. So it depends on the dimension of the matrix. So I have taken a sufficiently large one, x10 suppose. So this one is a standard way of writing the auxiliary function. What it is actually doing, as I said, it will just be finding out the largest component in terms of magnitude. Okay, so what I am doing, I am taking max1 as a variable and z as another variable. First I am initializing p as 0, okay. Then max1 I am taking the absolute value of x0, that is the first component I am taking as the max1. Then what I will do, I will check for the largest one. So this is a checking starting for I starting from 0 to I less than n. 0 to less than n means what I did said, n will be the dimension of the matrix. Suppose n is, so suppose the matrix is 5 dimensional, okay. Then you should start from 0 up to I less than n, that means 0 1 2 3 4. Suppose the matrix is 4 dimensional, then 0 1 2 3, like that, okay. So now is the check step, conditional part, ki if absolute value of xi is greater than max 1, what I have taken max 1 as the first component of the vector. If it is greater than this, then you replace max 1 by that absolute value, okay. Quite obviously, if suppose the third component is the largest one, suppose I am taking the first one as max 1, the second component is greater than this one, then max 1 will be the second component. Again the next step says suppose the third component is greater than the second component, then the third component will be replaced by the second component, and likewise it will go on, okay. So this is continuing ultimately for the entire length of the vector I less than n, because I0 up to n minus 1, okay. So once you get that, you just mark or store within p the component number, that means at which component, suppose third component you are getting the maximum, or fourth component you get the maximum, those this is updated at every step. So the ultimate one will be z equals to xp. So suppose the fifth, I am taking a 6 dimensional vector, so x6 is here, it is x6 in the dimension, okay. Suppose at the fifth component it is giving you the maximum, so p will be 5 in that case. Of a fifth component I am saying, so 4, because I am starting from 0, so p will be 4 in that case, and z will be x4, and so we have to return z. So this is the functionality of this auxiliary function. So once this is done with, what we will do, we will just repeatedly use it in our main program. So let us now enter into the main program. So for the main program, what we need to store the matrix which the user will be giving as an input, okay. We have to take care of the eigenvector. So as I said, I have taken x10. You may also incorporate the thing, you first ask for the row number of rows and the number of columns, okay, and then you can accordingly give this fix this dimension. I have, for the safe side, I have just taken a sufficiently large one, as I have said, okay. Suppose that now if I say ki I have given 12 cross 12 matrix, then this will not work. You have to replace it with 12. at least with 11, because 0 up to 11 it will run, okay, like that. And this R10 actually is taken for the iteration step vector, as we are calculating this xk plus 1 in the theory part at every iteration step. So that will be handled by this one dimensional array, okay. And this maxi error, all these are actually used to take care of the updation of this error level, okay. So let us now enter it. Once we enter it, we see how we are using it, okay. And what we have to start with, we are asking the number of row the user has to input, that is stored in capital N, because capital N is required, as I said, because how long will your loop run? It will run from starting from 0 up to capital N minus 1. So this a capital N is vital, it has to be stored, okay. So this is done, and then what will be stored? It will be storing the matrix, because this is obviously the fundamental thing on which we will be working with. So the user will be entering the matrix and it will be stored within this A1010, this at the two-dimensional array, okay. So this part is done here. And then what, you have to enter the initial approximation of the eigenvector, that will be stored in this xi dimension array, okay. And then what we'll be asking for, the allowed error level, okay. So I again just repeat it, though I have just separately said about, discussed about this in a separate video, ki if you have accuracy level demanded is, say, suppose 3-dimensional, then you have to take the error level 0.40 then 1. The justification I am not repeating here. If you have any confusion at this level also, please do just watch that video, you will get an idea why I am saying if I need 3 decimal places, you have to give the error level 0.40 then 1, not 30 then 1. I repeat, not 30 then 1, 0.40 then 1. That means 10 to the power minus 4 you should be taking instead of 10 to the power minus 3. If it is asked the accuracy level, you have to maintain is 10 to the power minus 3. That means 3 decimal places, okay. So whatever is demanded, accordingly the user will be giving the allowed error level, and he will be storing it within this AERR variable, okay. Achha, then this is the for the output part. Output will be printed, then you have to give the iteration number, because you have to calculate the, sorry, just we are counting the how many number of iterations are required. Eigenvalue, eigenvector, actually this is, you are creating the computation, the iteration table, okay, iteration table. Acha. Then what we will do, what will be there in the iteration table? In the iteration table, there is the iteration number, the eigenvalue, and the eigenvector for each iteration step. For each iteration step, which will be the eigenvalue, the largest of the component which you are getting from the eigenvector. For example, or for the justification here, as you may see, this is the computation table actually. This is iteration. This is the eigenvector you are calculating. Xk you are starting with. It is updated A into xk, whatever you are getting. Transpose I am writing because I have taken this row vector. Now I have to write it as a column vector or whatever. It just depends on how you are doing it. Okay. So that one, and mk plus 1 is the largest in sense of magnitude of this yk plus 1 components. So suppose it is a 4-dimensional 4 cross 1 vector. The third one is the largest, so it will be the third component. Okay, likewise. Okay, and then what will this xk will be? Whatever you are getting here, you have to divide it by this one. That means you are actually scaling this yk plus 1 by this one, so as to normalize it. Okay, then that will become the xk of the next iteration step. So this one is to be done there. Okay. So that is what we are giving for the first printing part, starting with, okay, iteration number, eigenvalue I have given it before, okay, no problem. It just depends on the orientation, how you just orient or write it or just represent it in the output part. So eigenvalue first, then eigenvector, okay. Acha. Then E equals to find max x. What is find max? Find max is the auxiliary function we have defined before x. What is x? X is the, you are starting with the initial guess. X is the array which we have already entered, taking the input from the user as the initial guess input. See here, this one. So I have to start with finding the maximum in terms of magnitude of the components of this x vector or x array, whatever you may say here. And I will store it in E variable. Okay. Now let us start with this one. While w equal to 1, the entire thing will run here. We'll see. I will just discuss what is the utility or what is the significance of this, taking this while loop little later. Let us now first enter inside and see what is happening inside this loop. Okay. So I'm just printing this ITR and E. Acha, ITR means the iteration step. The suppose I am starting with the initial guess, that is the first iteration step. So I have initialized this ITR integer variable as 1. So first it will print 1 as the ITR step, and E. That means the initial guess we have started with, if you recall back, till now we have not done any calculation, only have taken the input as the initial guess of the eigenvector and have calculated using the find max auxiliary function the largest of the component in terms of magnitude of that initial guess or initial eigenvector in the terms of E. So I will print E and ITR in the first step. So the first step of iteration is printed. That means this iteration step is printed, this one. Okay, only this one is coming first. According to what I have written in the program, this one is coming first. No problem in it. Suppose you give the initial guess 1 0 0 0 in case of 4 cross 1 dimensional vector, then what is your mk plus 1 1? Okay, like that. Acha. Now that part is done. Then what we have to do? We have to enter into the calculation part. That means A acting over or operating over xk, whatever initial guess you have started with. So this one is done inside this one. Okay, so first what we do, first we print it. Okay, that is the eigen. Here you have printed the eigenvalue, then we are printing the eigenvector. Okay, so as we have started with the initial guess only, so the whole initial eigenvector will be printed. So this loop actions ends here. Then start with this loop, there the calculation is done. Okay, so inside this loop what you are taking, you are initializing the s as 0. Okay, s variable as 0. Then for k running from 0 up to k less than n, that means the entire dimension of the matrix. Okay, what you are doing, s equals to s plus aik into xk. If you just see properly, this is nothing but the performation or of the operation axk. Because axk, if you do, say suppose A is a 3 cross 3 matrix and X is obviously in 3 cross 1 column vector, then how you will operate? A first row into the column vector, A second row into the column vector, A third row into the column vector, like that. So that is what actually is done here. Okay, so here this obviously you have the idea clear at this time or at this part. Okay, so let me just see here if I can shed some more light on it. So suppose this one is a matrix and you have taken a 4 cross 1 vector. So this one multiply this one. So what is actually changing? A11, A12, A13, A14. Say A11 multiplied with X1, A12 multiplied with X2, A13 multiplied with X3, A14 multiplied with X4. And all of them are added. Okay. So that is what you are taking place. Aik multiplied with Xk for every I. That means for every row. For I equal to 1, this will happen. I equal to 2, I equal to 3, I equal to 4. And each I, for each I, you are getting a component of the vector axk. So that is how it is constructed. So this part is taken care of here. Aik into xk. So every time you are just calculating it, you are adding it with s. And so s gets updated every time for this k running. Okay. So you started with s0. For the first component, it becomes 0 plus ai1 x1. Then in the next one, ai1 x1 plus ai2 x2, and this continues up to the entire dimension. Okay. And ri ultimately is equal to s. That means it is becoming the first component. Okay, for see properly, under this for loop, only this action is taking place. Only this multiplication part for the first component of the eigenvector is taking place. That means here, this one multiplied with the whole eigenvector is giving you the first component of the new eigenvector. Okay, so that one is being done by this for loop. And again for this I equal to 1, the next component of the eigenvector is calculated. Again for I equal to 3, the next component, and this continues. Okay, so Ri equal to S, whatever you are getting here. Okay, now once we are done with that, T equal to find max R. So again I am running the auxiliary function find max. Okay, so what actually it is doing, it is just calculating the maximum in terms of magnitude of the all the components of the eigenvector you have just created here. Because eigenvector created is stored in Ri, R, not I is stored, just I am saying I for the component part, but R as a whole is the one dimensional array in which the new eigenvector which is created, axk, is stored. So for that array is for that array we are running over that array this find max auxiliary function so as to find out the component, largest component of the R array. So that is done here and it is stored in the variable t. Okay, then next what we have to do, we have to normalize the vector. As I said, you have to divide the vector, not divide, but you have to scale the vector by the largest component, by its own largest component. So that is done here. Key scaling means what? Dividing every component by that largest one. So t is the largest one component. T is the largest component. That means t is the scalar by which you will be scaling. So and you will be dividing each component of the R array by t. So that is exactly done here. So the new vector xk plus 1, which will be used in the next iteration level, is given component wise by ri equal to ri by d. Okay, and I am initializing now max e, that is maximum error, to be 0. Okay, then inside this loop what I am doing, I am just first calculating the error. What I am doing, you see, for I starting from 0 up to I less than n, that means the entire dimension of the vector. Okay, error inside this variable, I am doing what? I am just, as I said, I am calculating xi minus ri. So xi is your guess, initial guess for the first step. And so suppose in the you are calculating this one, the iteration stable itr equal to 3, suppose, then it is the one which you have got in itr equal to 2, and this is the one which you have got in itr equal to 3, and you are just taking the difference of these two. For time being, as I have started with the initial guess only, so it is your initial guess minus the one which you have calculated here. Okay, the one which you have calculated normalized, this one here. Okay, that you are taking only, you are just concerned about the magnitude only, that's why you are taking the absolute value. Okay, now what I have to see, if error is greater than maxi, maxi as I said is the initial value of the error, you are initializing the error to be 0. Now if it is exactly the same what you are getting as eigenvector what is demanded, then it will become 0. Otherwise it will be having some positive value because you are taking your absolute value. So if error is greater than maxi, then you just store or update maxi by this error value. Obviously the difference is stored here, that is the deviation of the initial guess with the one that you are calculating till now up to this normalization part. Okay, and then what we'll do, simply I will replace the x array by the elements of the R array, because that will, as I said in the main theory part also, that will become the eigenvector to be used in the next iteration level. So the xi equal to ri I have to do. So if error is greater than maxi, then only this is required. Otherwise if it is exactly equal to maxi, then no need of replacing. Okay, so that's what is done here. So now my initial guess, I started with that which was given as an input by the user. Now it is updated by whatever my program or my method is calculating using the say AXK thing. Okay, so that's exactly the thing which is done here, as I said. Okay, so you started with an initial guess, you calculate AX of that, you calculate, you just scale it, and that becomes your new vector for the next iteration level. So this next iteration level is completed here. The construction of the vector for the next iteration level is completed here. Okay, acha. This now, after this completion of the next vector, the vector is ready to be used in the next iteration level. So what else we have to check? We have to check the deviation or the difference between the eigenvalue also. I said in the very beginning key I have to take care about the eigenvalue accuracy and also the eigenvector accuracy. Till now we maintained that we were just constructing the error level for the eigenvector accuracy. Component wise we are matching. See, I 0 up to I less than n means what? Your component wise you are matching. Key error is what? If any one of them is greater than maxi, then ultimately the largest of this error is stored in this maxi. Okay, acha. So this is done for the eigenvector part, but for the eigenvalue part we have not done anything yet. So that is done here, t minus e. Okay, so what was t? T was the largest of the component of the vector that you have created here. T was the find max r, means r you have created by multiplying axk. Okay, then the largest in terms of magnitude of that component of that vector, okay, was stored in t. So here now e was the error. Okay, you are calculating t minus e. Okay, and you see here e was also initialized to be, e was supposed to be 0 here. not 0, my mistake. E was supposed to be the largest component of the initial guess you started with. Why 0? Not 0. It will be the largest of the component of the initial eigenvector you started with. So that was E. And now you are creating a new eigenvector. So obviously we will measure the largest component of the new eigenvector and the largest component of the older eigenvector. Which one, what is the difference in between them? Because that will be the eigenvalue after all. The power method says that will be the eigenvalue after all. At the largest, at the iterationless step at which you are ending, the largest component of the eigenvector of that iteration step will give you the largest eigenvalue of the matrix. So that is, we have to check at every step. So suppose I started with x0 vector, the third component of it was the largest one. Okay, I recorded it. Then I go to the next level x1. Suppose the second component there is the largest one. Okay, then I will have to compare with them. Okay, so this comparison, so now if it is equal to, so suppose in the first step I have got the eigenvector to be 0.1, in the 0.12, the next step I am getting 0.123, and my accuracy level is 3 decimal places. So till now it is not matching, then I have to carry forward it. So in the next level I will check key, suppose in the next one, the x2, that is the iteration level 2, the eigenvector is coming x2, and so suppose the first component of it is the largest with the value 0.121. Then again there is some gap in between this 0.123 of the previous step and 0.121 of this step, and so we have to carry forward it until and unless the 3 decimal places thing is met up with. Okay, so that is the thing we are doing here. So we are just recording the difference in between them, these two, the largest component of the initial eigenvector or the eigenvector of the iteration level, say itr equal to k, and the largest component of the eigenvector of the iteration level at itr equal to k plus 1, say. Okay, and then you are storing it inside e equal to t. Okay, so that is now becoming this replacement. We are just updating the e's value. Okay, because e was the, what was e was the value of the largest component. Okay, at the iteration step itr equal to k, suppose, and t is the largest component of the eigenvalue for the itr level k plus 1. So this is the updatation of e. So e is now updated to be t. So that is the next level I will again use this value. Okay, now the last one, key, what I have said, key, I have to take care of both of the error level. So that is what it is done here inside this conditional loop. See, I am taking care of both of them. If error v value, that is the error value, error in the value is less than AER, that is the accepted error. Accepted error, if you recall back, it was given as an input by the user. Accepted or allowed error, whatever, and it was stored here. Okay, as I said, for 3 decimal places, you have to give the error level 10 to the power minus 4. For example, I am saying. So that is checked here. If the error value is less than the accepted error, and also the max E is less than accepted error. Okay, while max C, because here max C is coming from the eigenvalue, eigenvector part. Okay, so the largest component of this one here, you just see here, key, what I am doing here, I am calculating over the whole dimension, but each time it is replaced by the largest one. Okay, error was absolute value of xi minus ri for I equal to 0. Okay, if it is error is greater than this max c, whatever you are getting here, then max c becomes the difference between the first component. Okay, then again you run I equal to 1, again you calculate it. If it is less than max c what we have calculated before, that means the first component difference, then it will remain as it is, max c will remain as it is. But if it is greater than the first component error, then the second difference of the second components will be becoming your maxi, and this will continue. So ultimately I am taking the maximum, actually, you see, because it is updated every time. Okay, so that thing also I am taking care of here, this one and this one. If both of them are less than the allowed error level, then what will happen? Then actually we have to truncate, or we have to stop the programming. That means it will give you the ultimate largest eigenvalues output and the dominant eigenpair and the eigenvector, actually. Okay, so for that part, this one is conducted, only a slight check is there. Why the check? Because of the problem in the power method itself. As I said, the problem which I discussed before, for that I said if itr equal to 1, that means if in the first iteration level only this method is converging, that is an indication of some error or of erroneous part of the power method itself. So I said I will be introducing a check step so that the programming just warns you whatever you are doing, the might be the power method is not working properly. You start with an different initial guess. So for that thing, I am giving the check here, or inside the conditional loop, if itr equal to 1, then this will be the error message. Power method may not be giving the largest eigenvalue, may not be. Please do not write is not giving, because I do not know. It may also give, as I gave the example there. Okay. So may not be giving the largest eigenvalue, and run the program again with another initial guess of eigenvector. So giving this error message, the program will break out. So break. It will not give you any further output. Okay. So this is one thing. Else, if itr not equal to 1, that means more than one iteration is required for the execution of the program, then that is an indication ki okay, in this case is not coinciding with the error or the problem of the power method. Okay, so for that part, what we'll do, the normally the whole iteration table will be printed. Okay, so here this printing is done. The printing is obviously done before only. Here only the printing is done, because here in this step you are printing the eigenvector. Okay, acha. Then what will be given here, the last one key, the converges in how many number of iterations, largest eigenvalue. What is the largest eigenvalue? E will be the largest eigenvalue because it is updated every time with this t. Okay, as you just recall back, I said, so E will be the largest eigenvalue, this one. And whatever, what will be your eigenvector? X will be the eigenvector because every time it is also updated by the R array here. So X will be the eigenvector. So here it is. Iteration level, that means the number of iterations required, the largest eigenvalue, the eigenvector will be this one. Eigenvector means obviously you have to run an array again. So this is here. And then you give w equal to w plus 1. Now you can understand why I started with this while loop. See here, what is the condition for the while loop execution? W, if w is 1, then only this entire thing will run. So if w is not 1, then this will not run. Achha, this entire thing will run means what? This computation will go on. Achha, why we need the computation to go on? As long as accuracy is not reached. As long as accuracy is not reached, this computation should go on. But as soon as you get that accuracy, there is no need of running the computation. You have to stop computing. So this stop computing thing will stop when this while loop will not be executed, because as you can see, the whole computation is computed within this while loop, whole computation. So if I want to make my program stop this computation, then I have to change this condition so that this while loop condition is violated and no computation takes place. So that's why when this error level is already reached, that means error accuracy level, not my mistake, not error level, but accuracy level is already reached, this one, then I will obviously stop my program. So I will change the value of w to w plus 1. So it becomes 2. So as soon as, because w was 1 first, initialized to 1, you can see initialized, I think it was given above, initialized to 1 here. Okay, so I started with 1, I executed the loop, and ultimately I have reached the accuracy. It becomes w equal to w plus 1, so w equal to 2. So this will not be executed anymore. This will not be executed anymore. Okay, but if suppose this is not true, key error v and less than allowed error and maxi less than allowed error both are not true simultaneously, so suppose at least one of them is violated, what will happen? This part will not run, this whole if part will not run. This whole if part was doing what? It will, it was giving you the convergence, the ultimate output it was giving. Okay, so it will not be giving you the output. What will happen? Ki itr will now become itr plus 1. As I said, ki for suppose itr equal to 5, you run the whole thing and it is not matching. So this is not matching, this is matching, but this is not matching. So this is not, as a whole, this and condition is not satisfied. So as a whole, what will happen? This whole loop will not run. Whole loop will not run means this iterations is not doing, you are not getting the largest eigenvalue, more updatation is required. So that means I have to go to the next iteration step. So ITR become ITR plus 1. So as soon as ITR becomes ITR plus 1, what is about the value of W? W remains as it is 1, because this part is not running. So W is not updated. So W remains 1. So again the while loop will run. The while loop will run means what? Again the whole computation will be taking place. Again you will get this error updated. Okay. Again you will come to the check step. If it is matching the check this thing simultaneously, then okay. Otherwise again this will become ITR equal to ITR plus 1. So ITR equal to 5 was there, ITR equal to 6 is becoming, and again it will be done, and this could continues. Okay. So this is the thing. Ultimately when you get it, this part will run, this if part will run when this accuracy is reached, and when accuracy is, as long as accuracy is not reached, this else part will run. Else part is not given because it's ITR, else means ITR equal to ITR plus 1, and again this while loop running is your else part. Okay. So this is how we have designed the program. Okay. Acha. So first and foremost of all, let me just say ki, let us give one eigen first. Let us see ki whether this part is working properly or not. Okay. Acha. For that part, I am taking as an example this one. Okay. So already I have actually run this program, and this was the output of the program. See, this is a 4x4 matrix. So enter the number of rows. I have given 4. Okay. And now enter the matrix row wise. I was giving the matrix elements row wise. Then the initial approximation of the eigenvector. As I said, I am intentionally giving the eigenvector corresponding to the one of the eigenvalues 1, which is obviously not the largest one. Okay, because 2 is the largest one in this case. See here, 2 is the largest one, 1 is not the largest one. But I have given the eigenvector initial guess as 1, 0, 0, which is the eigenvector corresponding to the eigenvalue 1. So as soon as I gave that, what came here, enter the allowed error like this. I have given a sufficiently large one because I have not fixed there any accuracy level. When I give the accuracy level, you have to maintain that. Okay. So once you give that output, see, the first one is only, first iteration level is coming only. Convergence is mod iteration. And the largest eigenvalue is 1 here. Acha. Let me just say, actually here, I didn't give this check step. When I run this, I didn't give this check step. Okay. But if I give this check step, you will see ki this will not be coming. Okay. Let me run it for you. Okay. Okay. 4. Then let me introduce the matrix elements. 2, 0, 0, 0, 1, 1. Then let me just see what was the matrix. Last row. 0, 0, 1, 0. Okay. 0, 0, 1, then 0. Okay. Initial approximation, as I said, I will be giving the eigenvector corresponding to eigenvalue 1. You just see what happens. Okay. Error level, suppose I am giving, says as I gave the example just verbally, 3 decimal places. So I will be giving the error level 4, then this. See, this is converging in one iteration. So that is an indication ki, okay, my power method is breaking here. Okay. So obviously I have to start with another initial guess. So this error message is coming. See, it is not giving any output. The largest eigenvalue is this, the eigenvector corresponding to the largest eigenvalue is this. Nothing is coming because the power method is erroneous here. It is working erroneously. That should not be coming as eigenvalue. It should not be converging at this eigenvector only. So this output should not be coming. What is the output coming here? It is giving you the error message. Power method may not be giving you the largest eigenvalue. Run the program again with another initial guess of eigenvector. So let me follow this message what they are saying. Okay. So let me rerun the program again. Suppose now you see I will be giving another one where I'll be intentionally just giving you the eigenvector corresponding to the largest eigenvalue 2. There it is giving you the largest eigenvalue 2. Okay. But then also error message will be shown so that you will be prompted to give another initial guess. Okay. So number of rows 4, 1, 0, then 0, then 0. 0 1 then 0. Achha, as I said, I will be giving the eigenvector corresponding to the largest eigenvalue only. 0 0. Okay, and then error level, considering three-dimensional 3D, not three-dimensional 3D as the accuracy level, I am giving this one. So here you see, you are getting this one as your in two iterations only it is converging. Okay, you are getting this one as the eigenvector, and you are getting this one as the largest eigenvalue. Okay, in that case, because you are getting here more than one iterations. Okay, and also you may give other eigenvector also, where you do not exactly know what will be the eigenvector corresponding to the eigenvalue. So let me just show that one also. Let me just give say 0.5 for all. And then give again the error level as before. See, you are getting the largest eigenvalue corresponding largest eigenvector. Okay, up to 3 decimal places I have given the accuracy, so it is coming error here at the 4th decimal place. Actually, I have not given the output representation accordingly. This I have to maintain. Okay, I repeat again, I have not maintained it here, but whenever I give the assignment and I set the accuracy level, you have to give the output according to that accuracy level only. And I also have to mention up to those decimal places. If you can see in the question also, I have not just mentioned anything. Okay, I have just only mentioned you just perform it, whatever the accuracy level is, I have not mentioned it. Okay, so up to that it is okay, but whenever I set the accuracy level, you have to maintain it. Okay, so accordingly you have to make it here, the change you have to make here. Okay, this 7 I have given, not 7. We have to give if it is 3 decimal dimensional 3D 3 decimal places if you want, then obviously you have to change this accordingly. Okay, so this is it. So now you can have an idea how it is running. Okay, so let us stop here.